Shor's algorithm. So this particular circuit factors 15. Not so impressive. You get to know that the factors are 3 and 5. But still, it's an example of a quantum algorithm that does something that efficiently, that we can't do efficiently in a classical machine. I'll show more about this. If you want to know what it actually is, it's a simulation toolkit that we let our students use. So pass those around. It's ordinary electronics. So it's really a simulation toolkit. It implements parts of the quantum behavior enough so that we can run certain examples of a quantum algorithm. So quantum computers can solve certain types of problems faster than a classical machine. The typical question you ask is, I have this black box where I have a function. I don't know anything about the function. And now I'm going to ask some structural questions, an overall property of the function. And to do that in a classical machine, you might need to do very many function calls to the function to sort of derive the overall property that you're after. A quantum computer might need just one function call to do this. So you sort of extract the information from the function much faster than you can extract it from in a classical machine. And I'll explain more what's going on here. There are actually 3 kinds of quantum algorithms. So-called gate-based quantum algorithms, where you use similar gates as you would in a classical machine. They perform AND or XOR, addition, multiplication, that kind of thing. And you use these to solve problems from discrete math. Now, you can also simulate complicated quantum systems if you like. That's another use of them, but I'll soon show you another kind of, or mention rather, another kind of quantum algorithm that does that much better. This simulation task is really take a complicated physical system and simplify that so that you can find the important behavior of that complicated system. So what you typically see in this gate-based calculations is that problems where you need to use exponentially many calls in a classical machine might need polynomially or even as low as 1 function call to extract the overall information from the function. A problem here is that it needs gates with high fidelity. So it's really, really hard to build these things. One example is in Chalmers, where the WACT project, the Wallenberg Center for Quantum Technology, are building a quantum computer, and they're doing their best to reduce noise in that machine. You also need quantum error correction, a particular kind of error correction that applies to these kinds of machines. What I'll do today is try to explain to you how these gate-based quantum algorithms work and what they do. So I won't talk so much about the other kinds here. Adiabatic quantum algorithms are used more for simulating quantum systems. They can solve problems from discrete math, but then you need to rewrite the problem into that sort of computation regime. It's typically you have a complicated physical system that you want to calculate some overall property of. You simplify the system and put it into a quantum computer, and you extract the property you needed. You can do optimization with this kind of computer. And if you look at D-Wave's machine, that's what they do. They do optimization problems and get a speed up, not so large speed up, but still a speed up of the calculations. A problem for this kind of quantum algorithm is that we don't have good error correction. So it's still hard to do this. But if you want to buy a quantum computer today, this is the kind you can buy. The last kind is called sampling. You sample from a probability distribution that is somehow hard to calculate. It might seem it's a strange task, but the reason people are looking at this is that it's easy to prove that you have a speed up over a classical machine. That's really hard in the two first kinds. Part of my research, actually, how to really show that you have an actual speed up. That's simple here. Also, it's simple to build, simple architecture, so it's cheaper to build these things than the other two. And you can show more reliably that you actually have a speed up. Here, the problem is that errors removes the speed up for some probability distributions. As soon as we have noise in the machine, we can do as well with a classical machine as with a quantum machine. But like I said, this is just some sort of overview. I'll try to just talk about the gate-based quantum algorithms, what they do, and the reason they give you a speed up. So, a standard computer uses logical bits, 1 and 0, and logical gates, not, XOR, AND. You have several others also. You typically use voltages to just denote 0 and 1. And you build these from transistors in standard mode. The usual component here is CMOS. So CMOS technology. 2 transistors for a NOT gate, for example. More complicated functions are built in several steps. The reason I used XOR AND, you see the symbols here, the mathematical symbols, that's actually because they correspond to addition and multiplication. And that's what you need to do arithmetic. So if you've got these two, then you can do standard arithmetic. There are lots of results on what makes a complete set, but I don't want to go into that here. So, in the 70s, people realized that this kind of gates here will always emit heat. There's a lower limit to the heat that you must expunge on execution, and there's a theoretical principle that says actually the process that limits you is erasing data that costs heat, and here's the amount, Boltzmann's constant and the absolute temperature, and we're using bits. That's why it's ln2. So there's a law. You remember Moore's law. Moore's law says the amount of transistors that you can fit in a chip area doubles every 1.9 years. There's another law for energy consumption called Kuhm's law that says that the heat leakage per computation is halved every 1.6 years. Slightly faster. And here's a diagram with computers from the 40s until 2010. Interestingly, this is a straight line, so it's a log axis on the y-axis. So it's an exponential decrease in the energy, and it begins in the 40s, so before the transistor, which is neat. This Landauer's principle, Kuhm's law crashes into Landauer's principle in 2048, so not so far from here. Okay, so what do? Well, we turn to reversible computing, which was researched in the 70s. We are still doing this in the classical regime. You've got XOR, and you've got AND. Since it's supposed to be reversible, we actually need to preserve the inputs. We don't do that in the standard gates, but we do here. And the maps is really XOR for the bottom bit here, and XOR with the product. So you still have addition and multiplication. And you can build this in classical transistors 2, again in CMOS technology. And you can build your functions from these kinds of gates, but you don't have the problem that you erase information. So Landauer's principle is no longer a limit. Researched in the 70s. I'm showing you this because we'll use the same symbols in the quantum machine. If you want to build a complicated function, you can do that procedurally by just combining the gates that you have. Addition and multiplication gives you standard arithmetic. So this function here with these patterns of 1 and 0s can be built like that. Okay, there's a procedure to produce this. This particular function has the property of being balanced. There are equally many 1s and 0s here. Yeah? And now here's a task for you, which turns out to be pretty difficult. You have an unknown function, and you want to decide whether the function is balanced or constant. How many function calls do you need? Well, you need to test 1, 2, 3, 4, and even if you get 4 1s here, you still don't know if it's balanced or constant. You need to test 1 more. So half of the possible inputs. And if you add, if you extend the number of bits here, you quickly realize that the number of function inputs you need to send to the f is exponential in the size of the input. So a classical machine needs to do exponentially many calls here. That's really expensive. You need 1 more than half of the possible combinations. A classical computer needs this many calls. And I'll just tell you now, I'll try to explain how it works. A quantum machine, by adding certain gates here, will need only 1 call and can extract that information immediately, whether the function is balanced or constant. And that's the first example of quantum advantage. This is from the 80s. It's called the Deutsch-Josa algorithm. Okay, so how does this work? Why? What are these things? What are those things? Why? How am I representing data here? Something appeared here. What does that mean? Let me explain what it means, or try to. At least you should remember you don't need the entire table here. You don't even need half the table. 1 call is enough. So what do we use? In quantum computers, we use quantum states to represent our data. Quantum bits, 0 or 1. And it depends on how you build the machine. Whether you use electrical fields, or you use magnetism, or you use atomic states, or whatever. There are different technologies. I'll show you one here, which is easy to understand, I hope. Everybody's heard about polarized light. You know how polarized light works. If you got polarized glasses, vertically polarized light will pass through the glasses, and horizontally polarized light will not. Yeah? It'll be absorbed in the glasses. This is really useful when you drive at night, because reflections in a puddle will be horizontally polarized. Yeah? And they will be stopped by the glasses, so you don't see the reflections in water puddles on the road. Really useful. Here, what we'll do is we'll distinguish vertically polarized single photons from horizontally polarized single photons. We have a slightly more advanced filter here, which contains a mirror that will bounce off the horizontally polarized light, so we can detect whether there's a photon or not. So if there is a click in this detector, we'll say this photon was a 0. If there's a click in that detector, we'll say the photon was a 1. Is that okay? So, photon polarization, horizontal, vertical, 0, 1. And I've written it down as a vector here. We'll use vector notation. I apologize to those who aren't used to vector notation, but that's I need to assume something here. This is the math we're going to use. The reason we're using this is that what I'm actually talking about is the direction of the electric field oscillation. So it's a direction in space, so I'll use a vector to do that. Now, of course, electrical field can be superposed. This means that we can superpose these. We can add them together if you want. So if we do that, we get a different polarization. If I add these two, I'll get a different polarization. Depending on the phase, actually, I'll get a variation of the angle. So if I add 0 and 1 with the right phase here, I'll get 45 degrees in one direction. If I add in the other direction, I'll get a different superposition of the two, and I can just write down this is one superposition, that's another superposition. So we can superpose electrical fields. What would happen if I run this through my detector? Well, I would have probability 1/2 to get a 0 and probability 1/2 to get a 1. Equal probability between the two. In general, this is more advanced. I don't want to go into the details, but you could, in principle, combine them in several different ways using a phase, which I can choose. So it's actually a complex vector space, complex coordinates. But I'll stick to these combinations, those 4. That's the easiest way. So we have 2 different choices here. One usually is called the computational basis, 0 and 1. Yeah. But I could also use something we like to call the phase basis, where you combine 0 and 1 and you get a superposition or a different superposition. We still have 2 different alternatives. So you could see this as a different version of 0 and 1, if you like. Still a bit, yeah. And here is something I need to just state outright. In any calculation in a quantum computer, you can only access one of these 2. And it would take too long to explain why. The reason is called the uncertainty relation. It's a property of quantum mechanics. But yeah, it's like that. I have 2 alternatives for my bits. Typically I code into that, but I could also use these. So now I can just do the same kind of gates here. The map is the same. So this is the XOR, and that's the AND gate, or the multiplication. Same notation, same symbols, same map. Again, if you want to build more complicated functions, you build them in several steps. But note that we had new gates that I showed before, marked H for Hadamard. That's a name. The guy who first wrote down this. They change between these 2. Okay, so 0 maps to plus, 1 maps to minus. And it really is just a map of the electrical fields. Nothing more advanced like that. We have those in the lab at the university. It's a piece of glass. So that's really simple. These are not. Those are hard to build. But I won't dwell on that. So a C0 adds the control, the upper bit here, to the target. So if I have a 0 here, nothing happens. If I have a 1, it gets added to the bottom. Okay? Now, an important property of quantum computers is that quantum gates preserve superpositions. So now you might ask, what happens if I have a 0 on the lower one and this superposition here on the top one? Well, I can write it down in several ways. I mean, 0 plus 1 I should probably point using this for the online people because they can't see me. 0 plus 1 here, and 0 for the second bit. If you write that down in a bit string manner, 0, 0, and 1, 0, that's the input and the output. And you remember, if I had a 0 on the input, nothing happened. If I had a 1 on the output, that gets copied to the second one. So on the output, apparently I get this superposition. 0, 0, and 1, 1. Somehow, this calculation that this gate does is made simultaneously for this part of the wave function and that part of the wave function. So you can see somehow this is done in parallel. So that's called quantum parallelism. Okay? So if I have an unknown function here, and I send 0, 0, and 1, 0, so this is the input, and here's a space to put the target, the function value, I get 0 on the input and the function value of the 0. I get 1 on the input and the function value of the 1 at the same time. Oh, neat. I'm calculating this in parallel. Can we now check if f of 0 is equal to f of 1? That's actually the question I want to answer there. Is the function balanced? Then these will be different. If the function is constant, they will be equal. Yeah? So that's the question I want to answer. I have both function values immediately here. Oh, fantastic. Well, it's not that simple. I showed you this picture earlier. There are Hadamards in the beginning, creating a superposition of the input values. But there's also Hadamards at the end. What do these do? Well, the inputs, if I put a 0 through a Hadamard, I get a superposition of all the possible values. And you can see I'm writing n here for n bits. So if I do that, there will be a sum over all the possible values on the input from 0 to, well, as many bits as I have, all the values. All possible values are input at once to the function. The calculation is done in parallel to all of them. And then somehow the parallel results are combined by interference. That's the effect we use here to find the result. And that's the explanation you get in most courses on quantum computing. The interference gives you the result. What I'll tell you now is that this is not the best explanation. I'll try to tell you a different explanation that will explain better how this works. But then we need to look again at this example that I put. Quantum gates preserve superpositions. This superposition will get mapped into that superposition. So if I put a more complicated superposition here, 0 plus 1 and 0 plus 1 on both of the inputs, what will happen? Well, I'll get all the 4 possible inputs on this side. And you remember that 0, nothing happens if the control is 0. And if the control is 1, this will be added onto the second here. So they will switch order. But this is just a regular sum, so the order doesn't really matter. Nothing will happen to the output in this case. If I have a different superposition with a minus sign on the bottom here, that minus sign will appear here and there. Yeah? Because the second bit is 1 here and here. So that sign will end up here and there. Okay. Now what will happen? Nothing will happen here because the control is 0. Nothing will happen there. Here the control is 1. So this will be added on to the second one. So the order here will be 0, 0, 0, 1, and then that term will end up being this term. And now I can see here the order does play a role because the signs are different. Yeah. Okay, so let me reorder them so they are in the same order as before. It turns out that this superposition here is actually equal to this. If both are 0, you get a plus sign. If both are 1, we also get a plus sign. Yeah. Okay, this times that. Okay, so something happened. This is a different state than that. Something changed here. If I do all 4 of these, I will end up with this map here. Plus is on the input, nothing happens. Plus here and minus there. You have 2 minuses. That's what we saw just before. If I do the same thing here, minus, plus, nothing happens apparently. And here something changes again. Okay. And now you remember I told you that there was this transformation between 0 and plus. Okay. So if I do this transformation here, 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 and here, I will have 0, 0. There will be plus, plus here, and nothing will happen. So I'll recover 0, 0. Yeah. If I do the same thing here, it will be a 0 and a 1. It will be a 1 and a 1. Okay. And I can just do all of them. And it's slightly complicated, but maybe you can see what happens now is that the bottom number here will get added to the top. Yeah. All of these, nothing happens to the bottom bit, whatever. But the top bit will be changed if the bottom bit is a 1. Yeah. Okay, so what does that mean? It means that if you put Hadamard around this thing here, it'll turn upside down. Yeah. This effect is called phase kickback. If I put information in the phase here, this C0 will turn upside down. That doesn't happen in a classical machine. I mean, there is no phase in a classical machine. So the C0 is addition modulo 2 in the computational basis, but it's also addition modulo 2 in the other direction in the phase basis. So by switching between here, I can determine which direction the information will flow in, so to speak. So here's the simplest case. 1 bit input, that's the quantum algorithm that I showed you. And what we want to determine is whether this function here is constant, nothing happens, or balanced, something happens. Yeah? You remember I told you if I put Hadamard here, this turns upside down. If I put Hadamard here, well, I'll change from 0 to plus and then back to 0. Nothing happens, right? So just as if I had nothing. Yeah? A constant function is constant. It's a trivial observation. A balanced function does something. And when I put these gates, it turns upside down. So what was the idea of the quantum calculation now? Well, the idea is you insert these states here. And then you measure that value. If that's 0, the algorithm says it's a constant function. If that's 1, the algorithm says this is a balanced function. And the reason is the C0 turns upside down. So phase kickback is responsible here for the effect. So the standard explanation, it's an explanation, but it's not completely accurate. I would say it's not the best explanation. It's not wrong, but it's not the best. I mean, sure, all possible values are input at once. The calculation is done in parallel. You can understand it like this. The parallel results are combined by interference to find the result. But it's really important that there's a 0 here and there's a 1 here. That's not in this explanation. Yeah. It is crucial, but it's actually not part of the explanation. So what I would say is that there's a calculation made in this phase degree of freedom. Your quantum computer realizes this computation, and that's what gives you the structural information that you want to extract from the function. The Hadamard write this information into the phase degree of freedom. The quantum algorithm performs a calculation in F, which somehow puts the information you want in that degree of freedom here, and then you recover that and can read it off in your measurement device, in your detectors. So this is the reason. So let me skip that. In the forward direction, the function value is calculated. If you input x, you get f of x out. In the backward direction, you do a different calculation that really calculates the overall property that you want to reveal. So at this point, you could ask, what is calculated actually in the different algorithms we know of? You could ask, do all quantum algorithms follow this pattern? That's an interesting question now. Does this explanation always work? You could ask what data is used and what are the requirements on the system. And the answers is like that. What is calculated is structural information about F. I showed you an example if the function is constant or if it's balanced. But you could also extract something like the function period. How many steps do you need to take to get back the original value? The question, do all quantum algorithms follow this pattern? That's a definite yes. Phase kickback enables a quantum algorithm for something called a BQP complete problem, meaning that it covers all the efficient quantum algorithms. Not only the ones we know, but all of them. BQP complete means one problem that you could rewrite any other problem to. This is actually part of Niklas Johansson's PhD thesis, not so long ago. That was last year. So what data is used? Well, the lower system is the input, and the upper system is the target. If you put a 0 here, nothing happens at all, so you don't get any information. You need to put a 1 in this case to get some information. And what are the requirements on the system? Well, phase preservation, it really needs to preserve superpositions with the same phase. You can't have noise in the system, certainly, but you also cannot have a specific kind of systematic errors in the system. So it turns out it's really, really hard to build a quantum computer that preserves phase here. Probably won't have time or even your patience to explain how, but so if you write out the Deutsch algorithm in full, it looks like this. And it looks horrible, I know that. That's why I avoided writing this at first. It looks completely horrid, but here's a generic input S and T. And what happens here is a complicated calculation, and what you arrive at here is something that contains the Fourier transform of F. Those of you who are engineers know what the Fourier transform is. It's actually the discrete bitwise Fourier transform mod 2, but F hat. S and T are still in here, but the Fourier transform, that is structural information. For example, it contains the DC component, yeah, which tells you how large is the constant part of the function? And that's actually the information you're after in this case, the DC component. So the reason that this works is that you get the Fourier transform here. Everybody wants to know about Shor. What is Shor's algorithm? The one that's the poster child for quantum computing. Yeah. Shor's algorithm can factorize integers into prime numbers. And I'll just state here, the period of this function for a that you choose, well, you can choose a randomly. The period of this function here gives you the factors of n. And I could explain to you how that works. All you need is long division, but it will take 2 hours basically to go through all the math that you need, so we won't do that. I'll just say this period here is the number r, so that f of x plus r equals f of x. That can be used to factorize n. A classical machine does that in exponential third root of n. So it's really inefficient. That's how you break RSA. If you want to break RSA today, the generic number field sieve will give this number of operations. That's how you use it. The reason we use 3000 bits today for an RSA key is that we're this good at factoring. A quantum machine needs cubic number of operations. So n is in the base here, not in the exponent. So if we can build quantum machines, we immediately can just delete RSA from all our systems, because that wouldn't work anymore. Elliptic curves also. Anything discrete log will also go out the window. So it wouldn't be all that good for our machines. Here you use not the Hadamard, but the actual Fourier transform, discrete Fourier transform. So the Fourier transform and its inverse, and the calculation again looks pretty horrid. Let me just tell you what the result is. At the end here you will have an expression involving k, which is what you measure, the number k. So that's the output of the quantum algorithm. And the probability of measuring different k is given here. And you can see it looks like a Fourier transform. It has peaks, where you have resonance, and the resonance occurs for a particular multiple of the frequency. And r is the number we're after. So you have a high probability to get one of these peaks. Then you get a number which, well, is actually close to S over R. And the idea here is that you read off K, you calculate the closest S over R, and then you use your R to factor, and that's the idea here. The generic idea. And this can also be understood as a randomized phase kickback. You get a random number. S here is actually the random number from the lower input. So if you know what to look for, if you write S in here in the proper way, that will appear in the output actually. So you would recover the phase kickback. Right. I could tell you more details, but I think I don't want to. You could ask later on. Phase preservation is actually really hard to achieve here. It requires that this complex factor here is actually 1. I won't say more about that because we don't have time. So let me finish here. What we do in the group is that we've now found that it really is needed that we can read and write in an additional degree of freedom. And now what we're looking at is asking, what more do we need to actually achieve this phase preservation property? And there are all these funky names. Superposition and interference I talked about today. Entanglement, non-locality, and contextuality are quantum effects that we look at. The Nobel Prize was given to experiments that said, yes, quantum non-locality is what we see in our experiments. So that was the Nobel Prize last year. And we are looking at ways of incorporating this in our description. And I think that is enough for today. But of course, I'm open for questions. Thank you very much.
Thank you very much, Jan-Åke, for a decent going through on how this works. Do we have any questions in the audience, in the room or digital? And if you have digital questions, please write in the chat. Was it crystal clear? Yes? We do it with the microphone because then the people digital can hear.
Okay, so the question was the quantum computers that are built today, do they all use superposition and interference?
Yes, they do. I mean, that's the easy answer. Yes, because all of the algorithms use superposition and interference. Yeah.
Okay.
Thank you. More questions? No?
Nobody dares to ask.
Exactly.
Andreas.
Out of curiosity,
Yes.
if we are not talking about encryption, what will we use quantum computers for?
So the main use for gate-based, I mean, people point at Shor's algorithm and say, okay, we'll factor numbers, but I'm not sure that's all that useful, because for the reason that we invented quantum computers, they're looking at something called post-quantum cryptography, which is cryptography that doesn't use RSA. I mean, it's not weak to this kind of attack, basically. So I'm not sure that will be so useful, but the main use that I'm seeing is optimization. Optimization problems that where you get some sort of benefit from using a quantum computer. And often the benefit is not going from exponential complexity to polynomial complexity like we saw here. It's helping with the exponential difficulty, so you get a better behavior. But it doesn't remove the exponential dependence. It's also used in physics problems. If you want to solve difficult physics problems, maybe you can rewrite it so you can put it in a quantum machine and then solve it in the quantum machine. That's also the sort of short-term thing that we see.
Thank you. We have some questions in the chat. I think we take one for now, and that was, you mentioned D-Wave. What other major players like Google building the quantum systems?
The problem there is that the list changes all the time, but I mean Google, Microsoft, Intel, Toshiba, IBM, thank you, yes, and several other smaller players. Yeah.
We can take one more question here then. In what fields or areas will quantum computers make the biggest difference, do you think?
Short term, it'll be physics simulations, because one of the problems here is that we can't build large quantum computers, and most optimization problems that are interesting are so large you need to find ways to rewrite them into hybrid problems. A small part that runs on a quantum computer and a large part that runs on a classical machine, which is pretty common, but I mean the real short-term application is really physical simulations, I would say.
Thank you. And for those who are physical in the room, Jan-Åke will stay for a while, so if you have questions, please come forward. Otherwise, I would like to thank you with a big applause. And we hope to see you all again next Tech Tuesday, which will be the 1st of March. And for those who have their calendar ahead, it's not a Tuesday, it's a Wednesday. So we take a small change there. And the host for that Tech Tuesday will be Sick, and we will talk about smart robots solve challenges of the future. And just a little sneak peek is that this one won't be recorded because they will show some things that are not out of the market yet. So if you want to see it, you need to join in physical. A big thanks for today. Please, if you can help us throw the garbage, we would be very happy for that. And have a nice day. Thank you.